Okay, let's kick things off. When you look at a big industrial motor, the kind driving a pump or a conveyor,
Yeah.
that horsepower number on the side seems like the main story.
It does, yeah. It feels solid, like that's the power you get.
Right.
But especially in the tough world of industrial applications, that number, it's kind of, well, it's hiding a lot.
Getting what you
It's
say.
hiding the thermal battle, really.
Yeah.
For these big electrical drives, the nameplate rating isn't just about raw mechanical grunt. It's fundamentally about heat. Can the motor survive the heat it generates? Can it get rid of it fast enough?
So it's less how much power and more how much heat can it handle while making that power.
Precisely. Because if it overheats, that's it.
Yeah.
Catastrophic failure, we're talking major downtime, huge costs. So yeah, the real challenge is surviving the workload thermally.
Right. And that's what we're diving into today. We want to get past that simple horsepower number and into the actual science behind a motor's power rating. So our mission, for you listening, is to give you a shortcut to understanding this. We'll be looking at the thermal models, how motors heat up and cool down, and the 8 international classes of motor duty, S1 through S8,
Those are crucial.
and then the methods engineers actually use to figure out the rating when the load's all over the place, which, let's be honest, it usually is in industry.
Almost always. That thermal perspective, it's everything. I mean, if you had a load that was perfectly constant, same power, same speed, day in, day out rating, it is, well, relatively straightforward.
Just find one that stays cool enough.
Exactly. You find the size where heat generated equals heat dissipated, and the temperature holds steady below the limit. But like you said, that's rare. Most loads vary. Speed changes, power changes.
So you need more sophisticated tools.
You do. And the number one goal always is thermal. Making sure that motor can shed heat faster than it builds it up so it stays within its safe operating temperature. That temperature limit, by the way, is usually set by the insulation inside the motor windings.
Okay, so let's dig into that thermal limit first. Heat production versus heat getting out.
Right. The foundation.
You mentioned the continuous rating. That's the number most people think of when they see horsepower, isn't it?
It is, and technically that continuous rating is the power level where the motor's final temperature rise, let's call it theta, settles right at or just under the maximum allowed temperature rise, theta permissible.
And that term report comes from the insulation class.
Yeah.
Like class F or class H.
Exactly. Those classes A, B, F, H, they basically tell you the maximum temperature the insulation can withstand long-term before it starts to break down, degrade, and eventually fail. Sure. Higher class means higher temperature tolerance.
So how do engineers actually model this heating process? It's not instant, right? You switch it on, it doesn't immediately hit its max temp.
Definitely not. There's thermal mass involved, all the copper and iron. Engineers use simplified thermal models, often treating the motor like a single uniform block that exchanges heat with the surrounding air.
A simplification, but useful.
Very useful. So when you turn the motor on, heat starts being generated because of electrical losses, current flowing through windings, magnetic losses in the iron core. But the motor's body absorbs that heat initially. It has thermal capacity.
So the temperature creeps up.
Right. It follows an exponential heating curve. We can actually write it out.
Go for it. Let's see the math, but tell us what it means physically.
Okay. The temperature rise, thawafyi, at any given time after starting is roughly war.
We've got to break that down.
War is the maximum temperature rise it would eventually reach if you left that load on forever. It's the steady state temperature rise for that specific load. Think of it as the thermal ceiling for that operating condition.
And the other part, the exponential term with Tel1.
That part controls how fast it approaches that ceiling. Stall is just the base of natural logarithms. Tiet is time, and Tal1 is the crucial bit, the heating time constant.
The heating time constant. What does that physically represent? Like if I have a tiny motor versus a huge one.
Great question. Top depends on two things. The motor's thermal capacity, basically how much heat it can soak up, related to its mass, and how effectively it gets rid of heat, its dissipation rate.
So a big, heavy motor.
A really massive motor, tons of iron and copper, even if it has okay cooling, will have a large top head. It takes a long time to heat up because all that mass needs to absorb the energy.
And a smaller motor, maybe with really good fan cooling.
Much smaller tall. It heats up faster because there's less material to soak up the heat, and the aggressive cooling gets rid of it quickly. Its temperature reacts faster to load changes.
So large top means it's kind of thermally sluggish. It can handle a brief overload because it takes a while for the temperature to climb.
Exactly. It has thermal inertia or thermal memory, you could say. A short top-ton means it responds very quickly, good for some things, bad if you have frequent short peaks.
How is top on one formally defined?
Technically, top tom is the time it takes for the motor to reach about 63.2%. That's STON, no and E of its final steady-state temperature rise, top tom.
Okay. And this can vary wildly, minutes to hours.
Absolutely. Small servo motors might have a contour in minutes or even seconds. Huge multi-megawatt industrial motors could be several hours. It's a really critical parameter for understanding overload capability.
All right, that's heating up. What about cooling down? You switch the motor off or remove the load, the temperature drops. But again, not instantly.
Nope, same idea, just in reverse.
Yeah.
It follows an exponential decay curve. The cooling temperature, let's call it a tantra, follows a tun.
Okay, so the tannery is the temperature rise it started cooling from.
Right.
Tannery is time again.
Yeah.
And now we have tatanto, a cooling time constant.
Yeah.
Why? Tana just use tanjura again. Isn't it the same physical object?
That's a key point. Tottery, too, is often different from tottery, sometimes significantly different.
Why? What changes?
The cooling conditions change. Think about it. When the motor is running under load, its fan is usually running at full speed, forcing air over the cooling fins. That's maybe quite effective heat dissipation. But when you switch the motor off completely for a rest period, the fan stops. Now you're relying only on natural convection and radiation to cool the motor body. That's usually much less effective.
So it cools down slower than it heated up.
Often, yes, especially for fan-cooled motors. Or consider another scenario. Maybe the motor isn't switched off but just runs at no load for a while. The fan is still running, which helps cooling, but the internal heat generation is much lower because there's no output power. The heat flow paths inside change too.
So Tata 2 depends on how it's cooling fully off or just idling.
Precisely. A motor might have a long Tata 2-1 heat slowly, but also a very long Tata half cool slowly when off, because its cooling relies heavily on that fan action.
That makes sense. It's not just one number, it's dynamic. So for anyone designing a system, especially with start-stop cycles, you absolutely need to know both Tata 1 and Tata 2. A slow cooling rate means you need longer off periods to prevent heat buildup over cycles.
Exactly right. This whole exponential heating and cooling behavior is the bedrock. It sets the stage for understanding how we classify different types of work. The duty cycle.
Right, let's move into that. Because industrial loads aren't just on or off. They do all sorts of weird things.
They really do.
How do you even begin to standardize that? Comparing a motor that runs a pump 20-47-1 on, say, a stamping press that hits hard and then idles, or an elevator motor.
That's where the IEC, the International Electrotechnical Commission, stepped in. To bring some order to this thermal chaos, they defined 8 standard operating conditions, or classes of motor duty. They're labeled S1 through S8.
And knowing the S-class tells the engineer which thermal model to use.
Essentially, yes. It guides the selection and calculation process based on the pattern of operation. We can group them a bit. Let's start with the simplest ones, the steady state group, S1 and S2.
S1 sounds like the baseline. Continuous duty.
It is. S1 means the motor operates at a constant load for long enough to reach thermal equilibrium. Basically, its temperature levels off at that steady state value, the METM.
How long is long enough?
Typically, the rule of thumb is about 3 to 5 times the heating time constant, tall 21M. If a motor carries an S1 rating, it means you can run it at that rated load nonstop 24/7, and it won't overheat. Think of things like big ventilation fans in tunnels, or maybe pumps in a chemical process plant that just run continuously.
Okay, straightforward. Now, S2, short time duty. Sounds like the opposite.
It is, conceptually. S2 is for operation at a constant load, but only for a specific limited time, let's say 15 minutes, or 30 minutes, or 60-minute standard intervals. After that runtime, there's a rest period.
What's the key thing about that rest period in S2?
The crucial part is the rest must be long enough for the motor to cool completely back down to the ambient air temperature, $. It needs to reset thermally before the next run.
So each work cycle starts from a cold state, thermally speaking.
Exactly. Examples might be like an emergency water pump that only runs during a test or an actual emergency, then sits idle for days. Or maybe a valve actuator that operates for a minute, then stops.
What if the rest period isn't long enough to cool completely?
Then you're not in S2 anymore. You're moving into the next group, the intermittent duties, where heat starts to build up cycle over cycle. And that's much more common and more complex.
Okay, lead us into that. The intermittent periodic group, S3, S4, and S5. This sounds like where thermal memory really matters.
It's absolutely critical here. In these duties, both the on time and the off time, or rest time, are too short for the motor to reach its steady state hot temperature or cool back down to ambient. So it operates in a band of temperatures, ratcheting up over the first few cycles until it hits a stable cyclic pattern.
So the heat from the last cycle affects the starting temperature of the next one.
Precisely. S3 is the simplest of this group. Intermittent periodic duty. It's defined as a sequence of identical cycles, each containing a period of operation at constant load and then a period of rest.
Constant load, then rest. Constant load, then rest.
Yes. But here's a key assumption for S3. The heat generated during starting and braking is considered negligible. It's assumed the motor gets up to speed quickly and stops without significant braking energy dissipation.
When is that a safe assumption? When does starting heat stop being negligible? That feels like a judgment call.
It is a bit, but the standards give guidance. Generally, if the acceleration time is very short compared to the total cycle time and the load inertia isn't huge, you might get away with S3. Think maybe a simple conveyor belt that starts and stops periodically but doesn't carry massive weight.
But if starting takes effort or time,
Then you have to move to S4. Intermittent periodic duty with starting, it's basically the same cycle as S3 run at constant load then rest. But now, the heat generated during acceleration is significant and must be included in the thermal calculations.
what kind of applications need S4?
Things with higher inertia or frequent starts, maybe a large grinding machine or certain types of presses where getting the mass moving generates substantial heat in the windings each time.
Okay, so S4 adds the starting heat. What about braking?
That brings us to S5. Intermittent periodic duty with starting and braking. This is the most complex of these basic periodic cycles.
This is like it covers everything.
Pretty much the whole cycle.
Yeah.
You have 1, a significant starting phase, heat. 2, a period of constant load operation. 3, a period of rapid electrical braking, which can generate a lot of heat. And 4, a rest period, again, too short to fully cool.
Electrical braking heat, like regenerative braking where energy goes back to the supply, or dynamic braking where it's dumped into resistors, both heat up the motor.
Yes, even regenerative braking involves high currents and losses within the motor itself, especially during the transition. Dynamic braking definitely dissipates energy as heat, sometimes in external resistors, but often contributing to motor heating too. Reversing the power supply to stop is even harsher thermally.
Give us a classic S5 example where braking heat is a major factor.
Electric trains are a perfect one, especially suburban trains with frequent stops. Massive inertia to accelerate, starting heat, run for a bit, then rapid braking, often regenerative, to stop at the next station, braking heat, then a short dwell time rest, rinse and repeat, all day.
Wow, yeah. That motor is working hard thermally in almost every phase. Another example.
Maybe some types of rolling mills in steel production, like billet mills that have to rapidly reverse direction. The braking and reacceleration energy is immense. The motor rating is often dictated purely by its ability to survive those repeated S5 cycles without cooking itself.
Okay, that covers the intermittent group with rest periods. What about the last group? S6, S7, S8, continuous duty, but with variations. These motors never actually stop turning.
That's the key distinction. They remain energized. Let's look at S6, continuous duty with intermittent periodic loading. How is that different from S3?
S3 was load, then rest, motor off. So S6 must be.
Load, then no load. The motor runs at its rated load for a period and then continues to run, spinning, but with no significant load applied. It never gets switched off in the cycle.
Why is running at no load thermally different from being completely at rest? It sounds almost the same, minimal heat generation.
But it's quite different. At rest, S3, the copper losses, I2R31 augs, go to 0 because there's no current, and the fan stops, so cooling is poor, natural convection. In S6 and no load, the motor is still energized. You still have iron losses in the core, hysteresis and eddy currents roughly constant. You have some small copper losses due to the magnetizing current, but critically...
The fan is still running.
Exactly. The fan, assuming it's shaft-mounted, is running at full speed, providing much better cooling than when the motor is at rest. So the no-load period in S6 involves some ongoing heat generation, iron losses mainly, but also much better cooling than the rest period in S3.
Okay, that balance is different. Example of S6.
A press or a shearing machine is a good one. The motor drives the heavy load during the cut or press action, then it might run idle while the operator repositions the workpiece, then it hits again. It doesn't stop spinning between operations.
Got it. Moving on to S7. Continuous duty with electrical braking.
S7 takes away the rest or no load period altogether. It's a continuous cycle of run at constant load, then immediately go into an electrical braking phase like plugging or dynamic braking, and then immediately back to running the load, perhaps in reverse. There's no break.
Relentless. Examples.
Think of those reversing rolling mills again, where the steel slab goes back and forth repeatedly, or maybe certain large machine tool drives that need continuous rapid direction changes. The motor is constantly either driving a load or actively braking, always under significant thermal stress.
Okay, and finally S8. Continuous duty with periodic speed changes. This sounds like it covers variable speed drives.
It does. S8 is designed for situations where the motor runs continuously, but its speed and load are both changing periodically throughout the cycle. Think of, say, a sophisticated CNC machine tool running a complex path, or maybe a large centrifugal pump or fan drive where the speed is constantly adjusted to control flow precisely.
Why does changing speed add so much complexity beyond S7?
Because, as we touched on with cooling constants, a motor's ability to cool itself is highly dependent on its speed due to the fan. And its internal losses also change with speed and load in complex ways. So an S8 duty cycle requires a much more detailed thermal model that explicitly accounts for how losses and cooling capability vary as the speed goes up and down.
Wow. Okay, so just identifying the right S number, S1 through S8, is clearly the absolute first step if you get that wrong.
You're lost before you start. If you rate a motor for S3 duty when it's actually seeing S5 with significant braking heat, it's going to fail. Probably sooner rather than later. You fundamentally misunderstood the thermal load.
All right, so we've identified the duty cycle. Now, for anything other than the simple S1 or maybe S2, we have this fluctuating load.
Yeah.
How do we boil that down to a single rating? You mentioned equivalent methods.
That's the challenge, right? For those intermittent or varying duties, S3 to S8, you've got this complex pattern of loads and speeds. You need a way to figure out a single equivalent continuous load that would produce the exact same average heating effect over the cycle.
And simple averaging won't work because a short burst of high current heats things up way more than a long period of low current.
Exactly. Heat generation, particularly copper loss in the windings, is proportional to the current squared. That squaring makes all the difference. A current spike has a disproportionate impact on heating.
So we need to average the heat rate, not the current itself.
Precisely. And that means we need to use the root mean square, or RMS, value. This is why the equivalent current method is really the workhorse for thermal rating.
Okay, walk us through that equivalent current method. How does an engineer apply it? Let's use a hypothetical cycle.
Sure. Imagine a cycle with, say, 3 parts. Part 1. Starting current I dollars for time, T dollars. Part 2. Running current I dollars for time, $2 thing. Part 3. Rest period I3, I equals I dollars for time, $3 3. The total cycle time is TD equal T1 plus T2 plus T3 3.
Right.
To find the equivalent continuous current, I equal, that would produce the same total heating, you calculate the RMS value, you take each current, square it, multiply by the time it flows, sum those up, divide by the total cycle time, and then take the square root of the whole thing.
So the formula is I equals square frac sum IK2, T2 plus I32, T2 plus I32, T3, T1 plus T2 plus T.
That's it. Or more generally, IK equals square frac sum IK2, summing over all the k different parts of the cycle. That IK represents the steady, continuous current that generates the same average I2A losses, and thus the same overall heating as the actual fluctuating duty cycle.
And the goal then is to pick a standard motor whose continuous rated current from the datasheet is equal to or greater than this calculated.
Exactly. That ensures the motor you select is thermally capable of handling that specific duty cycle indefinitely without overheating. This method usually assumes constant magnetic flux and power factor, which is often a reasonable approximation for standard induction motors running near rated speed or well-controlled DC motors.
Makes sense. It directly tackles the I-2 relationship. But what about the other methods mentioned, equivalent torque and equivalent power? When do those come into play?
They're often used as, well, convenient shortcuts, especially if the motor speed doesn't change much during the cycle. If speed is roughly constant, then power is roughly proportional to torque. And if flux is constant, torque is often roughly proportional to current.
So you can just calculate an RMS torque or RMS power using the same formula structure, swapping T or P for I.
Yes, you can. You'd calculate TC or PK2P or PK2 phi dollar. It's mathematically simpler sometimes if you have torque or power data readily available.
But if time is the real source of heat, aren't these torque and power methods less accurate? Power involves speed, And the relationship between torque and current isn't perfectly linear, especially away from the rated point.
That's the critical caveat. You hit it exactly. The equivalent torque and power methods are approximations built on assumptions. They work reasonably well if the speed variations are small, but
If the speed changes a lot,
yeah,
like in S8 duty or during wide-range speed control.
then those assumptions break down badly. The motor's cooling changes significantly with speed, as we discussed, and the internal losses don't scale perfectly with just torque or power squared when speed and efficiency are varying. In those cases, relying on TIA dollars can lead to significant errors in thermal assessment.
So for high variable speed applications, you really need to stick with I2A or something even more detailed.
Definitely. Or you need to use more sophisticated dynamic thermal modeling software that tracks temperature changes step by step, considering the speed-dependent cooling and the varying loss components accurately. The simple RMS methods have limits.
Okay, let's flip this around. We talked about S2 short time duty. If I have a motor rated for continuous duty, S1, at power $2 per $1, can I run it at a higher power for a short time, like in an S2 scenario?
Absolutely. That's the benefit of thermal inertia, governed by that heating time constant total bulbs. If you only run the motor for a short duration, $2, it doesn't have enough time to reach its steady-state temperature limit to sink.
So it can handle more power for that short burst.
Yes. The temperature only climbs partway up the exponential curve. Engineers can use the heating curve equation, remembering that the theta itself is proportional to the power losses, roughly $2, to calculate how much higher the power dollar can be for a given short time, $2, such that a theta just reaches theta at the end of that time.
So a motor with a really long, taller dollar could handle a significant overload for, say, 15 or 30 minutes.
Correct. It might be able to handle, say, 150% or even 200% of its continuous power rating for a standard short time duty, like S2 15 minutes, provided it gets that full cooling period afterwards. The datasheet often lists these standard short time ratings.
So S2 duty lets you leverage the motor's thermal mass.
Interesting. But regardless of the duty cycle or the rating method, short time, there's another check needed, right? Peak demand.
Always. Thermal calculations tell you about average heating. They don't tell you if the motor can actually handle the instantaneous peak torque or current demanded by the load during the cycle.
What limits those peaks? It's not just heat then.
No, it's about mechanical stress and electrical limits. Too much instantaneous current can physically damage the windings or shaft due to immense magnetic forces. In DC motors, excessive peak current can cause flashover across the commutator bars, a nasty arc that can destroy the commutator.
Ouch. So there are hard limits on peak current Imax, even if the average thermal load is fine. Yes. Standard practice dictates maximum allowable peak currents relative to the motor's nominal rated current. For DC motors, you generally don't want Imax to exceed maybe 2.0 to 2.5 times a no.
And for AC induction motors, they're generally more robust.
They can typically handle higher peaks, but still have limits due to winding stresses and potential magnetic saturation. The range is often around 1.65 up to maybe 2.75 times IA, depending on the motor design. If your load cycle includes brief spikes higher than these limits, you must select a larger motor, even if the I-ferridoculation says a smaller one is thermally okay. Peak capability can override the thermal rating.
Okay, that makes sense. Thermal average and peak instantaneous are two different checks. Now let's bring in another factor, inertia. Usually we think of inertia as something bad. It resists acceleration, costs energy.
It does cost energy to accelerate, yes.
But you mentioned that it can actually be used strategically to help with these fluctuating loads, load equalization.
Absolutely. This is a really clever technique used for certain types of loads, typically ones with very sharp, very high, but short duration peaks. Think large mechanical presses, rock crushers, maybe forging hammers, reciprocating pumps, loads where the power demand spikes violently for a moment.
How does adding more inertia help? Seems counterintuitive.
You intentionally add a large moment of inertia to the system, usually by coupling a heavy flywheel between the motor and the load mechanism.
Okay, a big heavy wheel, what does it do?
It acts like a mechanical energy battery. During the parts of the cycle when the load is light, the motor provides enough torque to not only drive the light load, but also to slightly speed up the flywheel, storing kinetic energy in it, $12 J omega 2.
So it banks energy when demand is low.
Exactly. Then, when that sudden peak load hits, the press makes contact, the crusher hits a big rock. The entire system, motor and flywheel, starts to slow down slightly. As it slows, the flywheel gives up its stored kinetic energy mechanically to help drive the load through the peak.
Ah, so the motor doesn't have to supply all the peak power instantaneously from the electrical line.
Precisely. The flywheel contributes a significant chunk of the peak energy mechanically. The result is that the power drawn from the electrical supply by the motor remains much more constant, much smoother. The nasty peak seen by the mechanical load is effectively buffered by the flywheel.
So this protects the motor thermally by reducing the peak current draw.
Yes, significantly.
And it probably also helps the main electrical grid, right? Prevents those big voltage dips caused by sudden huge loads.
That's often a major driver for load equalization, especially in facilities with many such machines or on weaker grids. It keeps the electrical supply stable. Engineers calculate the required flywheel inertia based on the load cycle and the desired smoothness of power draw, often using the system's mechanical time constant in the calculation.
Okay, load equalization using flywheels sounds great for managing peaks. But let's circle back to that energy cost of inertia you hinted at earlier.
Yeah.
Starting energy.
Yes, the unavoidable downside. Every time you accelerate any rotating mass, you have to put energy into it. For an electric motor, especially an induction motor, a significant chunk of the energy drawn during starting is lost as heat.
How much heat?
There's a remarkably simple and fundamental relationship. The total energy dissipated as heat in the rotor circuit of an induction motor while starting it from rest up to its synchronous speed on no load is exactly equal to the final kinetic energy stored in the rotating mass at that speed.
So energy loss fracto 1,2 of J, A, or omega is 2,2, where J is the total inertia of everything rotating.
That's the one. D-airs includes the motor rotor inertia, the load inertia, and crucially the inertia of that big flywheel if you added one for load equalization.
Why is that simple formula so profound?
Because look what's not in it. The energy lost as heat in the rotor during starting depends only on the total inertia and the final speed. It does not depend on the motor torque, or how fast or slow you perform the acceleration, or what method you use for starting, like rotor resistance. It's a fixed energy penalty for getting that inertia up to speed.
Wow. So if I add a massive flywheel to smooth out my load profile and make the grid happy,
You are simultaneously guaranteeing that every single time that machine starts, you are dumping a larger amount of energy purely as heat into the motor rotor, or starting resistors if used.
that heat has to be accounted for, especially in those S4 start, stop, and S5 start, run, break, stop duty cycles we talked about.
Absolutely. If you have frequent starts with a high inertia system, those starting losses can become the dominant factor in the motor's thermal load, completely overshadowing the running load heat. You might have a motor that runs cool during its steady operation, but cooks itself just from the repeated starts because of that flywheel you added. It's a critical trade-off.
Okay, inertia is a double-edged sword. What about other factors? Environment, location.
Hugely important. These are often the first things you consider. Where is this motor going? Is it a hot, dusty factory floor, a clean, air-conditioned room, outdoors in the rain, a basement in the tropics?
And that dictates the type of enclosure needed.
Right. Do you need a basic open drip-proof ODP motor for a clean indoor space? Or a totally enclosed, fan-cooled IFC motor to protect against dust and moisture? Or maybe even a totally enclosed, non-ventilated TENV or hazardous location motor?
And the enclosure type directly impacts cooling, doesn't it?
Massively. An ODP motor allows ambient air to flow directly over the windings, which is great for cooling. A Tevica motor is sealed, and heat has to conduct through the frame to be removed by the external fan blowing over cooling fins. It inherently runs hotter for the same load or needs to be larger for the same power rating. So the required enclosure forces an initial adjustment or derating of the motor's capability right from the start.
Makes sense. Environmental protection comes at a thermal cost. What about operational factors, especially with modern drives? You mentioned variable speed earlier.
Yes, the rise of variable speed drives, VSDs or converters, has been revolutionary for control and energy saving, but it introduces significant thermal challenges, especially at low speeds.
Why is low speed a problem thermally?
Two main reasons. First, ventilation. Most standard motors, like TFC, rely on a fan mounted directly on the motor shaft. When you run the motor slowly using a VSD, that fan turns slowly too.
So less airflow.
Much less airflow. The cooling capacity drops dramatically at low speeds. If the motor needs to produce significant torque, and thus generate heat, while running slowly for extended periods, it can easily overheat simply because its built-in cooling system isn't effective anymore.
Was the second reason. Something about the VSD itself.
Yes, it's the nature of the electrical power coming from the VSD. Modern VSDs synthesize the AC waveform using high-frequency switching, like PWM. This creates a voltage waveform that isn't a perfect sine wave. It contains higher frequency components, or harmonics.
And these harmonics cause extra heating in the motor.
They do. These harmonic currents flow in the windings and induce extra losses in the iron core, things like increased eddy currents and skin effect losses. They're essentially parasitic losses that wouldn't be there if the motor was running directly from a clean sinusoidal mains supply.
So running on a VSD, especially at low speed, is a double whammy. The motor's cooling ability is reduced because the fan is slow, and it's generating extra heat internally because of the harmonic content from the drive.
You got it. That's the challenge. And the result is that a standard motor often has to be derated when used with a VSD, particularly for constant NORC applications at low speeds.
Derated meaning you can't get the full nameplate power out of it continuously.
Correct. You might have to reduce the allowable continuous torque or power output, sometimes significantly, maybe 15%, 20%, even 30% or more at the lowest speeds to ensure it stays within its safe temperature limits. Unless, of course, you add supplementary cooling, like a separate, constantly powered blower fan, often called forced ventilation or FVC.
So when specifying a motor for VSD use, you absolutely need to check the manufacturer's data for derating factors based on speed range and drive type.
Essential. Or specify a motor specifically designed for inverter duty, which might have better insulation, improved internal airflow paths, or integrated forced cooling.
Wow. Okay. That brings us through a lot of complexity hidden behind that simple horsepower number.
It really does.
Let's try and summarize the key takeaways from this deep dive. We've seen that a motor's rating is fundamentally about its ability to manage heat.
It's a thermal limit, first and foremost.
We started with that basic exponential heating and cooling model, governed by those time constants, Tauber 1 and Taut 2. That sets the physical boundaries.
And showed why cooling down can be different from heating up.
Then we navigated the 8 IEC duty cycles, S1 to S8. These provide a standardized language to describe how the motor is actually used from simple nonstop running in S1.
All the way to complex cycles involving starting, running, electrical braking, and rest, like S5, or continuous operation with varying speed and load, like S8.
And for those non-continuous duties, we learned that you can't just average the load. You need to use equivalent methods, primarily the equivalent current method using the RMS calculation, because heat depends on current squared.
Right. That RMS value gives you the steady current that produces the same average heating effect. And we noted the limitations of the simpler equivalent torque and power methods, especially when speed varies widely.
We also saw that you always have to check the peak current or torque against the motor's instantaneous limits, separate from the thermal calculation.
Can't forget the peaks. Mechanical and electrical limits matter too.
And finally, we layered on the modifying factors. How inertia can be used strategically with flywheels for load equalization, but comes at the cost of increased starting energy loss.
That crucial Fractiomegas-2 loss every single start.
And how environmental conditions, enclosure type, and operational factors like low speed or harmonics from VSDs necessitate dederating the motor's output.
It's a multi-layered analysis. Looking at just the nameplate, that's barely scratching the surface for any serious industrial application.
The sheer amount of work involved charting the duty cycle, calculating time constants if needed, running the RMS sums, checking peaks, considering D ratings. It really drives home why selecting the right industrial motor is a proper engineering task.
It is. You're predicting the long-term thermal behavior of this complex electromagnetic device under dynamic conditions. Get it wrong, and the consequences are expensive.
Which brings us perfectly to that final provocative thought, tying together the inertia and efficiency trade-off.
Yeah, that's a fascinating one.
We established that adding a big flywheel for load equalization is, technically, a really elegant solution, right? It smooths out the power draw, keeps the motor happier thermally during peaks, stabilizes the electrical grid. It seems like a win-win for managing those tough, spiky loads.
It solves the peak power problem very effectively, yes.
But we also established that the energy lost as heat in the rotor during every single start is unavoidable and directly tied to that total inertia. Franklin-Badu. More flywheel means more energy wasted as heat every time you press the start button.
An inescapable energy penalty for stability.
Exactly. So here's the thought to leave you with. If you have a machine with a duty cycle that involves very frequent starting, maybe an S4 or S5 cycle, starting hundreds or thousands of times a day, what are the long-term energy efficiency implications of choosing your motor and system based primarily on using inertia to manage those transient power spikes? Is the energy saved by maybe using a slightly smaller motor because the peaks are smoothed, outweighed by the cumulative energy thrown away as heat during all those high inertia starts over the machine's lifetime?
It's a deep question of optimization. Are you optimizing for peak power management and grid stability, or are you optimizing for total energy consumption over millions of cycles? They might lead you to different design choices, especially regarding that flywheel.
Right. Is the hidden cost of starting inertia something we sometimes overlook when focusing solely on conquering the peak load problem? Something to think about next time you hear one of those big industrial machines cycle up.